Shall we start? Everybody hear me? So based on Tim's advice in the last session, how many of you are actually considering going out and reading the Paxos paper? Don't do it. There's even a paper called Paxos Made Easy, which is actually harder to read. I wouldn't bother. Actually, it's one of the rare cases where some of the implementations in code are easier to understand than the actual written English. It's pretty unpleasant. So I'm actually going to rehash a little bit of that Paxos stuff a little bit later on, presuming that I speak at my usual pace. But first I have some lighter things to cover. Light but important. I realize I'm one of the last talks of the day. I am between you and alcohol, and I take that responsibility seriously. It's 30 minutes as opposed to the last one, so hopefully we can get through this, enjoy the time, and then go hang out at the bar, and we can do questions there, because I don't think we'll have time in the course of the talk. Okay. So many of you may not think of databases as having a moral code, but Cassandra very much does. And I'm hoping to be able to help you understand that today. Because Cassandra's moral code is the reason I love her. My wife calls Cassandra the other woman. And Cassandra's moral code has led to a really unfortunate image problem that we need to talk about. So we'll come back to the image problem later. First, I want to tell you the story that led me to fully appreciate Cassandra's moral high ground in the database world. First, a little bit about myself. My name is Matt Kennedy. I'm an architect at DataStax. You can follow me on Twitter at the tweet of Matt. Did I misspell it? No, tweet of Matt, that's right. And if you're interested in my interactions with the TV show At Midnight, follow me at Stinky Matt. That's not my work Twitter account. So in case it isn't obvious, I am the unholy offspring of Nick Offerman and Zach Galifianakis. In case you can't tell. By the way, you may have discerned from other talks today that those machines are useless, right? This is the one good thing you can do with a hard drive these days. If you take the top off, they have a really polished platter surface, and you can see it's good for doing the back of your hair where it's hard to see. You get one hard drive in front and one hard drive in back, and you can make sure you're not sticking up in the back. This is where I'm from. It's a backwater little planet. It's mostly harmless though, I like it. The reason I show this is that I came into the big data world by way of geospatial software development. Any other geospatial developers here? I was talking to one earlier. It's an exhausting discipline. And I was very relieved when I could get out of the business of just making maps with software. So 10-point bonus to anybody who knows what this map is. Anyone? I'll give you a hint. I have the key to what I will. There you go. 10 points. So I went to Georgetown for college. There I got a degree in computer science. Georgetown is, of course, most famous for its illustrious computer science department. But it's also somewhat less known for a very clever group of squirrels. Show of hands, how many of you have heard of the Georgetown squirrels? Good, because I just made this story up. So, Georgetown is faced with some very harsh winters. I feel like a complete charlatan saying this in Chicago, but for the mid-Atlantic, the sheer presence of snow is a bad sign, right? And for a long time, the squirrels on campus work together, and they store their nuts in a tree on campus for the winter so that they all have plenty of food. And this works out for a really long time. Squirrels are happy and fat, and then one particularly bad winter, some squirrels from American University make their way over to campus, and they borrow from the food supply. And this, of course, leads the squirrels to rethink their strategy. So as the spring thaw happens, one squirrel says, I've got an idea. What we're going to do is we're going to keep a ledger. Now, I will point out at this point that they still have a bit of an authentication problem since all squirrels look alike, but I leave that as an exercise to the reader. We can presume, I guess, maybe squirrels have names and that they're at a Catholic university, so maybe they're always honest about that. It's hard to say. So they go with this system where they add a ledger to their acorn collection. And this ledger serves them well. It allows them to, have some concept of acorns in and acorns out and who's supposed to get acorns, and they make sure that there's, kind of a fair distribution for the squirrels on campus. And of course, they account for the fact that there's got to be a squirrel running the ledger, and there's squirrels that go and fetch acorns, and there's squirrels that tend the acorn store. They've got that all worked out, right? And so this works really well until one spring, the tree gets cut down. And this throws their world into disarray, because the nut tree's gone, right? So what do? Well, so they observe that they've actually got multiple trees to use for their problem, right? And so this one squirrel says, you know what? I used to have this chicken friend, and he had this thing he kept saying about you shouldn't put all your eggs in one basket. And I think that for us, a basket is a tree. And I think we can draw this out so that if we put all of our nuts in different trees, we'll be safer. Our food supply will be safer. It's the right thing to do, right? And so the other squirrels kind of said, yeah, that sounds right. A whole bunch of nuts and a whole bunch of trees. What are we going to do about the ledgers, right? So that's going to be hard. So they had this huge squirrel convention to decide what to do. And they decided that as nuts are deposited at the trees, they'll still use the ledger, but a runner squirrel will take a copy of the ledger and copy that to other trees. And while he's at it, maybe he takes some nuts from that deposit with him and deposits them around the trees so they even nut distribution. So, but one squirrel said, wait, what if a tree gets cut down while a runner is on its way to it? Or what if the lawn is muddy and it takes a long time to get there and back? Or what if one of the trees has an intergalactic kegger going on around it and we just can't get to the tree? So the squirrels were divided on this. And some said that they didn't want to leave the depository until they got credit for their deposit. They're interested in the equity of their work. And the other squirrel said, no, the more important thing was to not waste time waiting for these acknowledgments that might be delayed for an indefinite amount of time and get back out there and get more nuts. So then a wise old squirrel asked, well, which is right? And the squirrels debated this further, and they said, on the one hand, depending on the conditions on the lawn, we may be waiting a very long time for this receipt acknowledgement process to complete. On the other hand, what if the ledgers of who has deposited what aren't in agreement? So they debated this for a while, and they weren't clear on what the correct answer was. So if we look at what they're debating, they're saying, okay, so the squirrel deposits the nut, and then they have to make this decision. The nuts go out, and the ledger receipts go out to the other trees, and then they come back. And so when does this squirrel get to leave? What if those return arrows take a really long time, or the arrows going out take a long time? So this debate seemed to not have a correct answer. And then one very clever squirrel piped up and said, oh, one more transition. There we go. What if something happens and we can't get to any of our trees? should we maybe team up with those pesky American university squirrels so that we have better geographic diversity in our food supply? So something catastrophic happening on one campus isn't likely to happen on the other campus. You know, we'll all have to gather more nuts, but that's okay. Nuts are easy to find, and the trees have plenty of storage space. So this was a clear win, and they teamed up with the American university squirrels so that everybody would be well fed over the winter. And all of a sudden, the answer to their initial quandary became clear. The distance between the two campuses is too vast to insist that all squirrels wait for complete receipt acknowledgement. So the correct thing to do is leave it up to each individual squirrel as to whether or not they want to wait for the full cross-campus receipt. Each squirrel is the best judge of how important their own work and time is. So each squirrel can decide for themselves, is it worth the wait? So this leaves them with a plentiful food supply that is resilient to any intergalactic keggers that might completely occupy the lawns of any individual campus for a period of time. And all of the squirrels are happy. Lessons. What does high availability mean? High availability means redundancy. The more of a particular thing we have, the lower our probability of losing it. But in order to do that, we have to distribute our stuff. And distributing our stuff comes with some additional challenges. We need to accommodate unreliable networks. We need to have different strategies for different path costs. And we need to plan for outright failures. But most of all, we need to cooperate. So before I get into the second half of the talk, I would like to point, and don't underestimate a squirrel with a Jesuit education. So before we get into the rest of the talk, I would like to point out that while I was doing this, I was obviously going to Google image search. And if you go to Google image search and type squirrels, there are some fairly obvious completions, cute baby clip art, but then there's squirrels with guns. Squirrels with guns is one of the top completions for people looking for squirrels on Google image search. And that right there probably says more about the state of the world than anything I have seen to date. And so, what are we really talking about? What's this image problem I referred to earlier? The image problem that plagues Cassandra is this term, eventual consistency. I'm going to anthropomorphize for a minute. Cassandra is widely rumored to be eventually consistent, as if she was some slacker college student that gets around to worrying about consistency when it's convenient to her. Eventually the laundry will get done, eventually the term paper will get written, eventually the mobile phone bill will get paid. This is an unfortunate and inaccurate impression. In fact, Cassandra is nothing less than the world's greatest pragmatist. And while these rumors of her being eventually consistent are true, that doesn't quite mean what everybody thinks it means. Cassandra is no slacker. Moreover, her eventual consistency is only one aspect of a much larger story, a story that gives her unparalleled worldliness and an unquenchable thirst for data. So, what's wrong with this term, eventual consistency? So the first problem with labeling Cassandra an eventually consistent database, pardon me for a second. I'm slightly under the weather and I have a tendency to talk ahead of my hydration. So the first problem with labeling Cassandra an eventually consistent database is that it excludes other classes of consistency of which Cassandra is capable. But we'll get to those later. Also, setting aside discussions of the word consistency for the moment, let's probe a bit deeper on the word eventual. In the context of distributed computer systems, Eventual is a term that describes some aspect of the timing or synchronization characteristics of a system. It is a fairly innocuous bit of jargon. But in the real world, where we spend the rest of our lives, it connotes laziness, passivity, and a complete disregard for anything that needs to happen on time. Like it or not, these negative connotations are attached to the term even when we should be thinking like logic-driven engineers. And this behavior can lead to imprecise conclusions about the sort of problems to which Cassandra is suited. Worse, inadequate research can lead decision makers to choose strongly consistent systems simply because they sound more rigorous. So Cassandra's eventual consistency is sometimes regarded as this liability rather than capability. Yet, Cassandra's ability to provide active-active multi-region data centers is always highlighted as a key strength and differentiator, as is Cassandra's ability to ingest data at very high write rates, regardless of active node or network failures. Both of these capabilities work as well as they do as a direct result of Cassandra's eventually consistent replication. So it makes little sense that eventual consistency should be derided as a weakness when in fact features that are considered core strengths completely depend on it. So it's useful at this point to consider what consistency means in the context of Cassandra. When we think about databases, the primary use of consistency that comes to mind is the C in ACID. Consistency in the context of an ACID transaction has to do with the database state at the beginning and end of the transaction and whether or not integrity constraints have been maintained. The meaning here is a little bit different. The consistency meaning in Cassandra comes from the distributed computing world. Cassandra spans these two worlds, distributed computing and the database world. And consistency used in the context of Cassandra is more aligned with the distributed computing meaning. Consistency in the context of Cassandra refers to different nodes having a coherent view of the same data. For example, suppose I add my email address to a table in a Cassandra database. In this example, the table is in a key space that has a replication factor of 3, so 3 nodes will need to be made aware of this change. Suppose that one of those nodes is rebooting because we just updated the kernel to get the latest security updates. My application can choose to proceed with writing my email address despite this node being down. When the node comes back up, its data won't be internally consistent with the data on the other nodes, but that's okay. Cassandra will eventually fix it. The important thing is that if it needs to, our application can always insist on seeing a consistent version of the record. So that's an important point. The notion of an application insisting to a database that it has preferences on how its data is handled is often a very foreign concept to newcomers to Cassandra. But it's a powerful differentiator from other databases. Cassandra listens to the needs of its applications, not just at the database instance or session level, but at the granularity of each and every operation. By taking advantage of this facility, operations can tune their consistency demands according to the logical tolerances of the application. They can achieve immediate consistency for write then read operations without sacrificing high availability. So immediate consistency of data is completely achievable in Cassandra without sacrificing high availability if eventual consistency isn't appropriate for some or all of the application operations. Can simply insist to Cassandra that those operations be immediately consistent. So in order to understand how this works, we need to look at some new concepts. So we have the replication factor, which is the number of copies of the elements of the data in the database, right? The replication factor is set on the database side, okay? The consistency level is a client-side setting that is changed potentially per operation. And a lot of times, newcomers to Cassandra tend to conflate these two concepts. Be careful about that, because it's easy to do. Consistency level and replication factor work together to help achieve what we need to from our application our application consistency needs. So let's take a detailed look at a quorum write then read, because this is important to understand. So the client makes a quorum write request, okay? And Cassandra receives that request at the coordinator node and sends that off. In this case, just to change things up, we're looking at a replication factor of 5 in this 6-node cluster, okay? So the coordinator node sends off the 5 replicas. And unfortunately, 2 of those nodes are down, right? So those can't complete. But we complete the request on 3, which happens to be a quorum of 5. And now we can return OK on the write. So what happens when we go to try to read that data back? So we see we've got 3 nodes that have the data, right? And our failed nodes have now come back online. So now 2 of those nodes that had the data crash. Or maybe we're just doing some maintenance on them. So we send this quorum read request. And the quorum read request gets to the coordinator, and it sends out 3 requests to data to nodes that should have the data. And it doesn't send it to the nodes that it knows are down. So we get back answers, and the first one responds with the data and a timestamp on the data. And then we get answers back from these 2 nodes that don't have the data, but that's okay. Quorum doesn't mean that we have to have a quorum of nodes that agree on the same data. What it means is that we have to check with a quorum of nodes to make sure that we see at least one node that was a part of both the write and the read, right? And that one node's timestamp wins. So now the coordinator says, I don't know what to do because these other 2 nodes don't have data, so I'm going to return this latest timestamp and return that value back to the client. Okay. So having achieved immediate consistency, we might think that we never need to worry about eventual consistency again. Not so fast. So what about our replicas from that last example that didn't acknowledge the quorum write request? We still need a way to make those nodes consistent with the other nodes, eventually. And there's also the case where we don't care about immediate consistency. So this is true if you have a particularly high write rate workload. And perhaps you are writing data to record it, never necessarily intending to read it back. So you might be extremely satisfied with the high performance of a consistency level 1 write because your read is not going to be dependent on the immediate internal state of the cluster. So the way we keep Cassandra internally consistent is with mechanisms like hinted handoff, read repair, and anti-entropy repair. Repair is a horrible, horrible naming convention for what this is. It's very unfortunate, and we're talking about changing it, because repair makes it sound like, oh, my node crashed, I need to run repair on it. But really, repair is a health operation, right? We have to run repair on the cluster, because what we're doing is we're taking care of these brief windows of period where maybe not all the nodes could acknowledge all the writes. We're making the state internally consistent so that it is more efficient in the future for client nodes to see consistent views of the data when they need to. So we just looked at Paxos in Tim's talk, but we'll look again because it never hurts to hear these things repeated. Linearizable consistency is a new category for Cassandra, though. We're used to thinking in terms of eventual consistency and tunable consistency, but Paxos adds a new aspect to consistency, which is this notion that some things should happen before this other thing. So this is variously known as compare and set, check and set, lightweight transactions. An important note here is that if you are using lightweight transactions to access a table and do particular types of write operations, you need to use lightweight transactions for all of those kinds of writes. Because if you go and do a regular write operation, you can squash any in-flight lightweight transactions that you expected to be serializable. Furthermore, that consistency level that we talked about, serial consistency level, has a multi-data center version and a local data center version. You need to be extremely careful with this, because if you insist on local serializability, and there are operations going on in 2 different data centers on potentially the same data, if we're only using local serializability, those could also squash each other, okay? So, don't bother understanding the Paxos paper. Understand how to use Paxos in Cassandra. It will be time much better spent. If you want to read up on the ticket, 5797 is the JIRA to refer to. So, in short, this is allowing us to say put X in the database if X is not already in the database, right? So we can say set foo equals bar if foo equals baz, or set foo equals bar if foo equals faz. It might not be immediately obvious why this is useful. So let's go through the hot new social media application Monster Mash. So this is a game where players create monsters that compete to see who can mash potatoes the fastest. The game allows players to create monsters with different attributes to help them mash faster. Each monster has a name, but it needs to be unique. So it goes without saying that this is the most popular game in the world, so it absolutely has to use Cassandra as its database. Now suppose 2 players, Alice and Bob, want to create a monster named Stinky. They create their monsters as they see fit, and when the monster is ready to be saved to Cassandra, they have to provide a name for the monster. If they both choose Stinky, then without serializable consistency, we have a problem. Prior to Cassandra 2.0, Alice and Bob's Monster Mash clients would perform a quick check with Cassandra to make sure the name isn't taken. That's what we see here. It's not taken. And then they would both write the record. But if they write at the same time, then Alice might see that her monster was saved, but in reality, Bob's monster can come along right afterwards and overwrite, overwrite Alice's creation of Stinky. So now Bob owns Stinky, and Alice doesn't understand why she lost her monster. So, how do we fix this? Okay, so we say, does Stinky exist? And Stinky does not exist. So now we're going to do a lightweight transaction insert, okay? And we're going to say, create Stinky if Stinky does not exist. And these both come in at relatively the same time, but thanks to lightweight transactions, Bob gets a denial, right? This is important. The application is the thing that is enforcing that every user has a good experience. And so now, Alice got there first, she gets to name her monster Stinky, and Bob doesn't. And things are now working the way they should. So this gets us to this kind of complete set of consistency capabilities in the database. Tunable consistency, linearizable consistency. The important thing is that Cassandra is honest with the applications, and the applications are honest with Cassandra. They get to tell each other what their needs are and have those needs met. So you hear us say a lot that Cassandra is the most honest database out there, and you know, these are kind of some of the reasons why. So in Cassandra, we sometimes hear you know, mutterings in the marketplace. Well, what do we do with Cassandra and eventual consistency? I can't have a database that's eventually consistent. But really, there's also some jealousy of Cassandra's other features that really require eventual consistency to work. So it's important to note this. The consistency mechanisms are king. High availability, tolerance of node failures, tolerance of data center failures, tolerance of network failures between data centers. Cassandra stays as resilient and highly available as it does because of the consistency mechanisms. Cassandra isn't Cassandra without eventual consistency. So we like to say Cassandra is a key, or consistency is a key value. Get it? It's a NoSQL joke. Always-on big data demands multi-region DCs, just like our squirrels demanded multi-campus nut storage to keep their food supply safe. Multi-region DCs must face the reality of network partitions, and they also have to be sensitive to the fact that clients local to DCs don't want to pay geographic penalties to perform their operations. Eventual consistency enables applications built on Cassandra to do what they need to do correctly and flexibly while maintaining constant availability. That is it. We have 2 minutes for questions. Are there any of those? Yeah.